Hey guys, what's up? Eddie Alho here with KissAnalog.com. Hey, if you're here to learn about power supplies, well, you came to the right place. We're going to look at the flyback converter. Where's that board? I pulled up a board the other day. Maybe I'll pull it up right now. Kind of last minute thought. Anyway, basic flyback converter. Okay, we're going to just jump right in this. We're going to show you some signals over here on the board. And I want to show you what I'm going to show you. We're going to look at the gate drive. When you start up a power converter, one of the best places to start looking is right here, or the drain. I like to look at the drain sometimes. Sometimes there's been issues looking at the gate because there's a problem. So if you look at the drain, you know the gate's working because if the thing's turning on and off, you know that it's turning on and off. Then you want to go look at the gate just to see the quality of the gate, right? So yeah, when you first start turning on a converter, you'll have multimeters all over the place maybe. Simple thing like this, you have a multimeter over here looking at the output voltage so you can see if it pops up. You'd be wanting to monitor this as well, okay? You want to make sure that the circuit, the rectifiers and everything's all wired correctly, that you're getting a positive voltage here. So when you first start cranking it up, you're looking for a positive voltage and you go, okay. And then you're watching for current too. You want to make sure the current just doesn't take off on you, because if you want to start off the low load, minimum load over here, something, not a no load probably. No load's actually a harder thing for a power supply. So you put a minimum load, just something to drain off things. You want to drain off the circuit so that it can supply power, especially on a forward converter. But even on a flyback, you want to have some kind of load on it, okay? So minimum load over here, you start bringing up the voltage. I can tell from my volt box over there if it's pulling current. I can kind of hear it, and I'm also watching for it with a Hioki meter. I'm going to show you the setup real quick. Then we're going to start looking at some measurements. And here's the measurements we're going to look at. We're going to look at the drain, but we're going to start off with the gate because I've already looked at the drain. If you saw my little short video, was it one of those 1 minute shorts? I don't even think it's full minute. Anyway, I did a quickie just to kind of show you what you might be looking at, and wondering if you knew what we were looking at there. But what we're looking at is the drain, and we're also looking at the transformer output. Kind of fun. So what we're going to start today, we're going to look at the same things, but I'm going to start off looking at the gate. Okay, I'm going to show you what that looks like. From that, we'll see if we have a nice gate drive, nice square gate drive. We'll also see if we have, and I'll be looking at output meters and all that kind of stuff. But okay, so with you guys, I'm going to start off showing just one signal. Normally, I would have maybe something here, or maybe just something here, maybe something over here, and I would have a couple, probably 2 or 3 scope probes up here, maybe a current probe at the input even. So, but for now, what we're going to do is we're going to look at this, just see what this control chip, this PWM pulse width modulator chip does. Okay, we're going to talk about terminology and all that kind of stuff, like switch mode power supplies, SMPS. Okay, all right. So this is a flyback converter. To be more specific, this board I have, this eval card from Texas Instruments, is actually set up currently for an active clamp flyback converter. Really cool converter, okay? If you're doing a flyback converter, you probably want to do an active clamp, all right? But it's set up that you can also change some circuits. I have to solder, do some things to change it so that it's a typical flyback. Now, this schematic simplified, I'm going to show you the real schematic here in a moment too. But right here, essentially what it is when you're turning off on this inductor, this transformer, it really acts like an inductor. You turn it on, the dot's up here, so this is positive, so this is negative. This diode's turned off. So you turn it on, you let go, and then the polarity switch instantly, right? So this, let's say I had 180 volts here, peak here in the US from 120 volts input. Let's just say it's around 180 volts. I would have roughly twice that here, okay? So because I'm going to have the 180 plus, I'm going to have the 180 that got charged on the inductor, but now it's flipped around. So now I got 180 here from the inductor. So the inductor is like a little battery. So 180 plus 180 from the VN. So twice. Plus there's some leakage inductance. We're going to get into that stuff more later. So we don't want to get hung up on those every minute detail right now, because those are the more minutiae. That's, you know, drilling down. Okay. But having a top view understanding is the most important thing, and then understanding details comes later. All right, so it's KISS, right? KISS analog. Keep it simple, right? So you turn this on, turn it off, and this guy turns on. Okay, so this guy turns on, dumps energy from the transformer, the inductor, and I call it an inductor because it's holding a charge. Transformer doesn't build up a charge and release. A transformer would be like forward converter. If the dots are both here, I turn this on, this guy immediately gets forward biased, so the charge is coming off as I'm developing it. That's a forward converter. Flyback's inductor. Charges up an inductor, and then you turn it off, and the inductor, all that flyback, all that kickback energy gets released to the secondary side. Okay? And we're going to talk about how to design this another video down the road. But first, we want to, you know, do some fun stuff. Look at the converter, get a good feel for how it works, and then, like I said, then we'll work on the details. So we have a bulk capacitor here that stores up the energy. So then this will hopefully maintain a DC voltage with a decent amount of ripple, low amount of ripple. So I've shown the ceramic because I did just the 2 plates, didn't show plus, I didn't show the curved plate, so it's not aluminum electrolytic. I mean, it probably is in a real circuit, but I'm just showing it as a ceramic. Anyway, so there's the circuit. We're going to start off looking at this, okay? And we're going to look at the pulses. The pulse width probably modulate. Even though it's a minimum load, it'll charge and discharge a little bit as it, you know, as it tries to regulate the output, okay? And then we will look at the voltage here at the drain. We'll see how that voltage doubles. And then finally, we're going to look at the voltage right here before the diode. So we're going to look at the square wave right here. This is going to be a square wave. It doesn't turn into DC until we get over here. Okay? It's actually AC voltage, right? It's galvanic isolation. We're creating a square wave. The return, what we're going to call ground on this side, we could call this ground and give it a negative voltage if we wanted to. It's isolated, so we can do anything we want with this energy and this voltage that we're developing right here. We can put the ground symbol up here and call this the negative voltage. And we could have 2 of these coming off the transformer, have one positive, one negative. Hey, there we go. We have an audio amplifier. 2 voltage rails, right? So the other thing is, in this board, which I'm going to show you in their schematic, there's another winding on the primary side. This is a primary power, secondary power. Terminology again. So over here, primary ground, secondary ground. Over here we'll have another winding that's, you know, typically I show primary windings going this way, secondary windings going this way, but you don't have to. You could show it here, wrapping around to this side. So you want to generate a voltage to power this chip, to have more efficient power, because otherwise you have a high voltage DC over here, say 180 volts. You have to drop 180 volts down to say 12, 15 volts down here to, for that chip. Even if it's only a couple milliamps with that voltage drop is some power. That's crazy. It's crazy to have an efficient power supply than have some stupid linear regulator over here dropping power, right? So yeah, we don't do that. This is called a kickstart. We kickstart the circuit. Once the circuit starts running, then we have a bootstrap that we just call it a bootstrap. We just strap on another winding off this transformer, goes back there. Hey, we're learning all kinds of terminology, huh? So kickstart circuit, starts it up. It burns a little, it's not efficient, but hey, it's okay. Now here's the thing, as chips like this one has been around and developed, they've made them more efficient kickstart circuits, because often you'll see the kickstart circuit as kind of linear regulator, a transistor with a Zener diode to clamp the voltage, and you'll put a regulated voltage in this from here. But in this case, they're just using a simple resistor off of this because it doesn't take very much current in this chip to get it going, because it's a UCC. Whenever you see the double C, it's a CMOS. They don't take a lot of power to get going, okay? So that's the advantage of a chip like this, is it gets going with minimal circuitry over here. But now if for some reason this didn't get going, there's not enough current to keep that thing running either. So if it doesn't start up, you kind of know where to look. Well, you don't know where to look. This could be shorted over here. But anyway, yeah, if things don't run off right out of the bat, you want to look at the voltage over here on that chip. So, okay, let's come over here. Let's, first of all, just take a look at that voltage, okay? And then I think we'll look at the drain voltage as well. And we'll also look at the real schematic for this. I'm going to point out these things on the real schematic, as well as that bootstrap winding. I'm going to show you how that works too, okay? So, this will be a good video. We're getting our feet wet. All right, let's do it. All right, guys, so that is the board, and our input power is right here. Goes to the fuse, EMI filter, rectifier, bulk capacitor. This is our main transistor that I showed on that whiteboard, our main transformer I showed, and the control chip that drives the gate of that FET, okay? So we'll look at the gate and the drain of that FET. The drain's over here with this differential probe set. That's those. And this is the gate right here, these two guys. And then over here, this guy and his other probe, which is hard to see down here, he's looking at the output of that transformer. So he'll look at that, he'll be looking at the output square wave, okay? So that's what those things look like. Here's the probes. That's the one that's on the gate. This guy's on the drain, and this guy over here is on the output. And that's the picoscope. I just reviewed that scope. If you didn't see that review, I used this board to show some signals. So you might see some more signal stuff on that video. And here's my MacBook with the Pico software running on it. And you'll see the waveforms on that just shortly here, okay? Okay, coming over to the meters, this is the X-Tech. I reviewed this not long ago, actually. So that's looking at the output, using those right here, this probe right here. So that's looking at that. I got the amp probe, you know, company, if you don't know them, they've been around forever. As long, I think longer than Fluke, but they're owned by the same company that owns Fluke. It's looking at the AC voltage right here, the input. And then strapped across here is the Hilke, which is ready to go to sleep on me because he's tired of waiting. So, and he's going to be looking at the current coming in. All right. So I'm going to kind of monitor that as I rotate this dial. I got the power on. So all I have to do is rotate this and bring up the voltage. So what you're going to see is the scope. Okay. So let's do it. All right, guys. I just wanted to show you that I do use a blast shield, you know. So I like to, I'm pretty safe, but I like to capture shrapnel before it hits my face. And I'm wearing these safety glasses as well. And, you know, as far as jewelry goes, I'm not touching this stuff with power on. So I'm not concerned. I'm going to be using the scope, and I'll make measurement changes I'll make the measurement changes with power turned off. All right, guys, it's go time. Got everything going, ready to power up, and here we go. Once I get over 90 volts or so, we'll see a waveform turn on over here. And there it is. I'm going to freeze that. Okay. All right, so we're on the picoscope, and here we go. This is the gate, right? Now I've got some measurements selected down here. For one thing, you can see the maximum voltage, so it'll pick like a peak up here if it sees it. It's 11.71 volts, so yeah, I was expecting somewhere around 12 volts. That's kind of what you shoot for. You're driving the gate of a FET. Hopefully the gate of the FET is turning on down here somewhere. And so you don't want to drive it too much voltage because it's inefficient, because you're charging the capacitor and discharging the capacitor at the gate. But at the same time, you want enough voltage to drive it hard, to really force it on, okay? So typically 12 volts is a good target. Now let's zoom in on this guy. Well, here, let me show you the rest of the waveforms down here. 282 kilohertz. So we're switching frequencies 282 kilohertz. That's a nice switching frequency. What else do we have? We have duty cycle. It's not 50%. It looks close, but it's about 43.77. That's just based on our load. We have a pretty light load, okay? And what else do we have? Cycle time. Oh, yeah, this is just the inverse of the frequency. This is kind of a, I think I was going to do the rise time of this waveform. Let's just change that measurement out real quick. Let's do the rise time for more fun. Let's do this one. And I'll get rid of the cycle time. We can do the math on that. There we go. So there, now it was hidden down below. I just had to scroll up and down to see all the waveforms. Or I can come over here and hit the small just in case you don't know, and then it'll have more room. But I kind of like the medium. Shows some of the statistics here. But yeah, so what, rise time is about a microsecond? I don't know about that. Here, you know what? I'll tell you what. Let's zoom in on this guy, okay? I'll zoom in on this rising edge. So it's got, a little bit of stuff going on. I can move this window. Let me see. I could actually get better vertical resolution because I can make this scope go to 12 bits if I want, instead of the typical 8 bits that many of these scopes have. And anyway, so that's the rise time. But this is like, here, I can zoom in on this a little bit more. And what do we have here? Here, let me get these rulers over here, okay? They call them rulers, the cursors. Let's turn those on. And I'll bring one of them right here about, the other one right about there, I guess. And then up here, it says 6.9 nanoseconds. Yeah, I don't know what that 1 microsecond stuff is all about. And in that time, it changed 7.14 volts. So, all right. And incidentally, see this 143 megahertz down here? This might be, if this rise time, you see these peaks here, results in some EMI stuff, it could be right around that frequency there, just to give you a pro tip. All right, so let's back off on the zoom, and let me move this window over here. I love how you can move the windows around. Let's look at this ringing over here, okay? I'm going to zoom in on this whole waveform to begin with, and let's do that again. Whoops, sorry, got to hit the plus sign. And I got to stop grabbing cursors. Actually, I wanted that cursor over here. So this cursor is at 3.5 microseconds. You see, this one's changed. So I could say, hey, bring this one over to 3.6 microseconds. So I can get them both over here. So I don't have to zoom back out and grab it. Then I'll grab this guy. And, well, you know what, I'm actually, sorry guys, I think what I want to do, I'm just kind of looking at the resolution here. Not sure why it doesn't seem like, okay, so here we go. Sorry, just looking at this frequency here as it turns off. There's a little bit of ringing. Now guys, I'm using differential probes. This frequency 70 meg. I'm using differential probes, so when you're really looking at this stuff in detail, you want to be really careful the kind of probes you're using and so on, because you want to be careful with the loop inductance of your probes, okay? So differential probes are great to look at bigger things, but this frequency stuff, we don't want to get too hung up on that right now. I'm just kind of zooming in and kind of showing you things you would look at. We would use some times 10 probes to look at these things. But I'm using differentials because I'm going on both on primary and secondary side of the circuit. So just makes it easy. All right, so I'm going to turn these guys off, zoom out, and say, yeah, there's gate waveform. Great, awesome. And by the way, this channel D, the yellow waveform, and if you're not used to the Pico, 20 volts is up here, minus 20 is here, so that's why it shows plus minus 20. I'll show you that. That's how it works, is plus minus system instead of volts per division. So we have 4 volts per division, 4, 8, 12. So just wanted to point that out. Across here we got microseconds here, 4 microseconds, 2, 0. Right here's my trigger. That's why it's 0 there. I can grab this and move it around. It's one way I can control the trigger. The other way is to go up to the menu. So anyway, just giving you an idea so you know what you're looking at when you're watching this screen, okay? All right, so now what we want to do is all these other 3 probes are off, okay? A is on my drain, so let's turn that guy on. And I'm going to turn on manual because I want to manually select this. If I put it on auto, it'll find which one of these things to put it in. But I just want to say, yeah, let's use 500. Okay, so now we got those 2 channels turned on. And by the way, the trigger, I will show you the trigger menu. So I was triggering on D, the gate, and I was triggering right at this threshold. And I got an advanced trigger. I could change that to single edge just to simplify things so you guys, so that's the simple rising edge trigger that you're used to. Okay, here's a threshold, 4 volts like I said. Pre-trigger is 20%, that's because I'm to the left of center. So, and it's on auto. Just to give you an idea, and we're 2 microseconds per division. Alright? And also, let me see what my 80s, so I've got this maxed out. And if I go to buffer, I got that maxed out 2 gigs, so maxed out everywhere. So alright, and I got full bandwidth. I don't have any filtering or anything, okay? So now let's go ahead and recapture this thing. And we're ready to go. I'm going to bring up the voltage. And we should see it triggering, and there it goes. So I'm going to just freeze this again, drop the voltage so I don't have to worry about things going on and popping while I'm talking. So here's the thing, I'm not really using the full grid of the screen right now, but yeah, there's the thing. So look, when the gates turn on, this yellow waveform, see over here on the right side of the screen we got our grid for our yellow. It's 12 volts right here. So as it turns on, the drain, the voltage, the transistor turns on, right? So the transistor is shorted. It's short right down here. Then when the gate turns off, then the voltage on the drain pops up. And we can see it pops up to almost 300 volts. Okay, let's take some measurements of that. And that's channel A. All right, let's measure maximum voltage on that. Okay, let's just see what the max voltage goes to. And here we are, 282 volts. Now I can zoom in. I can hit the magnifying glass. I can zoom in on, capture one wave of each, partial of the next one, so you can see the off, on, off, on. So put this down here where it's not in our way. So yeah, you can see as the gate goes up, the drain drops down, and the drain drops pretty quickly. There's a little bit of a, see that guy right there? Right as the gate starts to go up, it's turning things on, and then when it meets a certain threshold, this little blue thing drops off. So here I can zoom in on that just so you can see what I'm talking about. And it's kind of choppy looking, so maybe I will go to the trigger, because I mean we got a lot of volts per division and we're kind of zooming in, so I'm going to make this a little bit smoother. Go like 9 bits resolution. And down here on the C, if I go too many bits, I can get some filtering because it filters the bandwidth. It limits bandwidth when you go too high. So on this guy here, whoops. Okay, there's that one. Let me go to DSP, and we'll make this one 9 as well. Okay, that should be smooth. Okay, so I'm going to get rid of this window. All right, so I'm going to recapture it, okay? So capture it with that new 9-bit resolution. Let's turn that on. All right, running nice and smooth. The other thing, guys, I'm not really filling the screen up very much, so it's not the best use of the A to D processor because it has to slice up this whole screen, and I'm only using a portion of it. But I'm just trying to, I guess, make things easier on myself. Well, I was trying to make it easy for you guys to see this screen. So anyway, there we go. So it looks a lot better, right? A lot better, a little smoother. We got a little bit more voltage resolution. So you can kind of see as the gate turns off, right here at the bottom, it starts to, it's where the FET's really starting to turn off completely. And that's when this blue line, the drain, shoots up. And so during that time, there's a little bit of stuff going on, you can see. So that's the kind of stuff you worry about for EMI. Same as this, when it comes up in rings. Now, this is the gate, the yellow one, so we're not as worried about that. We can, again, these aren't the probes, so we don't want to get too hung up on that right now, okay, because we're looking at differential probes. But what I want to point out is, here, let me move this yellow guy down out of the way. What I want to point out is, look at this blue waveform. Look how smooth it is on the drain. Now, if you've looked at flyback converters before, you'd be super impressed right now, because normally you'd have some ringing on this thing. It would look more like this gate. It would look worse, actually. You'd see some ringing, all this stuff going on, and there'd be snubbers that kind of try to control that stuff. With an active clamp flyback, it makes this thing look incredible. So that's why it looks so great. So I kind of wish I had two boards so I could just flop them back and forth so I could show you the difference, because soldering and desoldering parts going back and forth is kind of a pain. But I will do that in another video, so you'll see a regular flyback and you'll go, wow, okay, let's go back to the active clamp. So there you go, guys. There's those two waveforms. I wanted to show you those, okay? Now, okay, let's do this. Let's go look at the schematic here, and I want to show you. See, this looks a lot more busy than my whiteboard, right? Here's a control chip right here, okay, down the left corner. So try to filter all this other stuff out of your eyes. The thing on the left's EMI filter comes up, bridge rectifier up at the top left corner, bulk capacitor C7 right here. So that's where that voltage comes into my whiteboard, okay? And then it comes over here to the transformer. And all this jazz right through here, a lot of this stuff, a good portion of this stuff is the active clamp, which is basically a filter, a snubber across the winding. So just ignore that for now. Just look at this winding here. There's the dot. So plus, when the transistor's turned on, the dot's plus. Okay, so current's going to come through, and this inductor is part of this active clamp, which, again, we're going to talk about that stuff later. So it comes through here through the FET and through this sense resistor. This is how you sense the current. When the transistor is turned on, this is how you sense the current going through. And you just have a small value resistor. It's actually a 3-watt resistor. This could be a through-hole resistor. Today, with surface mount, we would probably have 2 or 3 resistors. You derate them big time so they don't run hot, so they don't change values. They last, they're dependable. You don't want them burning out on you. And then you pick off this pick-off point right here. See, it's current sense. C sense comes down here, goes through a RC filter. So this 1K, 2200 picofarad. There's your RC filter. Okay, this guy right here is kind of a load on. It's a voltage divider, and it kind of loads it down. But so the voltage coming off this thing is too big. It looks like. I mean, I'm reverse engineering right now because I haven't gone through the math and looked at this, but that's what it looks like to me. We got 3K, 1K. So 1K's, what ends up here is about 3/4 of the voltage you started off with, right? So what's nice about having a 1K resistor is it's a pretty large value. So you got and 2200 puff is actually a pretty large value here. So you got a really good filter for the current sense. All right, so that's what's going on here. And they even have a Zener diode here. Well, this is a Schottky, I think. And the reason why I was going to say it looked like Zener, but it's a Schottky. The reason why you put a Schottky here is you never want the voltage here to be reversed more than, you know, half a volt or something to protect this chip. Okay, so that's what that's for. So we've talked about current sense. I wasn't really going to get into that, but I'm kind of showing you a little extra because the current comes through here and then it goes back to ground, back to this capacitor, kind of in a zigzag way, but it goes back to the bulk capacitor. This bulk capacitor and the filter, the capacitor that's in parallel with it, which, you know, the way it's drawn, it's kind of hard to see all this stuff, but to me it looks like this cap right here. Okay, so C7, C21, they're going to be placed pretty close to this transformer and the right here, the return side of this sense resistor. So that loop, you want to make it short as possible. Okay, that's your power cycle loop, your switching loop over here, and that causes EMI. You get all kinds of parasitics, inductance, capacitances, and stuff like that taking, you know, jumping in. So you want to limit that stuff as much as possible. So that's why that loop's nice and minimal. So we just saw the gate and we just saw the drain. The drain looked awesome. So let's go look over here on this secondary side. See this? Here's our diode. They actually have two in parallel going to a bunch of bulk capacitors, okay? And this all looks like aluminum. You know, they're all polarized, so it doesn't even look like they have high frequency filtering over here, which is kind of interesting. And then up here, there's a RC. It says not used, but this is your snubber across this, okay? There's no snubber there, so we're going to expect to see a little bit, maybe not such a great waveform, because over here we have this active clamp acting like a snubber. Over here we have no snubber. Oh, and by the way, primary winding up here, secondary winding down here. So dot up here, this guy turns on, he's positive. This guy is going to be negative, non-dot right here. The dot's positive, so the non-dot's negative, so you can see it's turned off. So when it turns off, reverse polarity, and then we see this go in a reverse polarity and it charges up these caps. Okay? Meanwhile, we have another winding right here. So this line right here is showing isolation barrier. Here's the optocoupler, voltage feedback. That's what all this stuff is. So when you break things down, you know, circuit elements down to what they are, what they're doing, it can simplify the schematic because all this stuff right through here is just voltage feedback. Okay, this is used for common mode filtering. But anyway, this guy right here is all feedback, and you go across the optocoupler so that you have galvanic isolation from secondary to primary side, and you can tell this control chip what's happening over on this side. Okay, so we're going to talk about that stuff later too, but right now we're going to talk about this winding, this third winding. That is your bootstrap winding. You notice the dots at the ground again. So when we got positive up here, the positive's on the ground, so nothing's happening. When it turns off, then it flybacks here too. So both of these guys are flybacks, and this flies back, charges this bulk capacitor. Look, it's only 0.1 mic, so it's really small bulk. You know, some high frequency stuff for sure. Now it's low power running this chip, so it doesn't need a lot. But over here we have 100 microfarad. So what happens is you do a little filtering. You got this 20 ohm resistor, which gives you a RC filter, so you get nice clean power to your over here, your VDD pin. Right there should be this line goes up to that dot right there. And I like the way they drew this, so there's not a four-way intersection. Those are no-nos, see? They're doing really good. Whoever drew this schematic did a really good job not showing four-way intersections. But they did kind of miss a little line right there. So what happens is when you first turn on, you got this kickstart. The current comes down here through this 47K 2-watt resistor. So that's why it's 2 watts, because it's going to have a little power for for a brief moment. And it comes down to VDD. When it starts up, this thing starts to charge up this capacitor, and this diode here keeps the current from this to go back feeding into all, this stuff. So it just keeps you a nice isolated voltage over here, and it also keeps this voltage from going into here too. So you got a a lot of times you'd have another diode from this kickstart voltage, but in this case it's just a high ohm resistor. So this diode helps protect things so you're not tying two voltages together. But you are. This one here is going to take over because he can supply a lot more current than this 47K can, so the current will come from this guy into VDD, and very little current will go in there. This voltage will be a little bit higher, and we'll have very little current going to this guy. This here is our bootstrap circuit. Okay, so there's our bootstrap. All right, so let's go look at the voltage over here now. All right, so we're back at our scope. I'm going to turn off the zoom and turn this guy back on and turn on this waveform. This guy should be, yeah, this guy's our other differential probe, so I got set times 20, okay? But we're going to be looking at the output voltage. I'm going to go, I think it's 12 volts, so I'm going to try 40, see if that'll work, okay? And let's do it. I just click on the screen and that window goes away. All right, guys, so now we're going to power up and we're going to look at all three of those voltages, see how they relate to each other and all that kind of stuff, and should be kind of fun. We'll see the polarities and all that kind of stuff going on. All right, so let's do it. Hey, you did notice how high that voltage on that drain of that FET was, right? Wasn't just the voltage coming off my 120 volts rectified to 180 volts. It was like 300 or something, right? So, and I'm not going all the way to 120, so maybe I should this time. All right, yeah, I think I might do it. So let's crank it up and capture. There we go. Look how steady that is. That scope's awesome. Okay, I'm going to freeze it, turn off the voltage again, and there we go. So our yellow and blue one we saw before, and let's see what the blue one is this time. 289, almost 290 volts to the peak. There's 300 right there. So that clamp is doing such an excellent job keeping that voltage down. Instead of being popped up real high like you'd see in normal flyback, it just takes all that energy and pushes it down through the whole top of this waveform. So yeah, wish I had a normal flyback to show you side by side, but look at this green one. That's what, you know, without the snubbers, that's what it looks like. So pretty bad, huh? Okay, you know what? I might be able to do something here to simplify things. This is pretty cool. Go to views. Yeah, I'm going to add a scope view. Okay, let's see, on scope 2, I'm going to turn off the gate. So we'll look at the drain. So down here, we're looking at the drain, and I'll shrink these down just to make them small. It didn't really do a lot for us, did it? Yeah, that didn't change anything. Oh, that's because I have this window open, I think. So, and then up here in scope 1, so in this one, I'm going to turn off channel C. Okay, so there's, okay, I'll click in here, and let me see if I can make that, yeah, now it made it bigger. All right, so up here in this scope waveform, we have that waveform we saw before, the gate and the drain. So this is gate and drain, you know, inverse of each other, right? When gate turns on the FET, pulls it down low. So the drain pops up when the gate goes low. Okay, guys, so just to cover this thing up here. Now, look, I went ahead and I named our signals we're looking at: FET, drain, the gate, the secondary, and you know, just kind of go into this thing. I'll just show you one of them. Just go in here, display, type it in. So pretty easy. Anyway, so I just did that just so it's a little more obvious. Then it also puts it on measurements down below. It's pretty cool. Yeah, so I have gate on both waveforms, both windows, so that we can compare the same waveform to each thing that's going on. So this is the drain of the FET on the primary side, and this is looking across the transformer on the secondary side. And you can see the ringing going on here, and a little bit more noisy because this does not have that snubber installed, where over here we have the active clamp. So otherwise this blue waveform would look more similar to this green waveform. Okay, so let's just walk through this again. over here up on top, the gate turns on, so it pulls the drain down, transistor's turned on, and then the gate turns off, the transistor pops up the voltage, but it goes up to almost 300 volts. Down here it says 290. Down here it says 292.9, and that's because it's got the voltage coming in off the bulk capacitor plus the voltage on the winding. So it's the voltage on the winding has been reversed, and so we end up with this high voltage. But because of the active clamp, it's kind of smoothed out and looks nicer. So when we go down here, what we see is the waveform, the winding on the secondary side also got reversed, so now it's positive and the diode starts conducting, and so this is the voltage that's being sent to the secondary side. So now we're going to regulate some voltage over here. It's, you know, on and off, then on. So the capacitor on the other side of the diode is going to smooth this out and average it and all that. But what we see here is when the gate does turn back on and the that's when the transformer gets energized, and so the dots get reversed on the secondary side and on the primary. So when the gate turns on, that's when the so the gate turns on, the transformer is energized over here, it's pulled down, current's going through it, it's charging it up, and so the dots on the other windings are reversed, so they turn off. This is the negative winding. So whatever energy was left in the winding when that happened, it just kind of rings. And we're going to talk about where this comes from and all that stuff as time goes on. But it just kind of rings, and then first it's high frequency, and then it kind of goes in this low frequency ring, and then it kind of dampens out until it turns on again. The primary side was turned off, so then all of a sudden now the secondary side gets to charge again. So that's what's going on over here. And you know, this number would help EMI, that kind of thing going on down here. We'd have to look at the capacitors and see what's going on the other side. It's possible this might not cause an EMI issue. Now what we can do is hit this thing here, and we can come zoom in on this just so we can see what it looks like. Take this window, move it over here. So yeah, that looks pretty nice. Now remember, I have 8 plus 1, so I've got 9 bits instead of 8. So I've got more vertical resolution, and so I can zoom in on this waveform and, you know, see more detail. So anyway, that's just kind of an explanation and a picture of what's going on and how you can use your waveforms on your scope to compare to see what's happening. And yeah, this is just kind of a starter. Okay, now you know what? Let's go back to views. I want to show you one more thing that might be kind of neat. Let's go to scope 1, and we're going to turn on all 3 waveforms back up here. Okay, and then I'm going to, on this one, I'm going to actually get rid of this view. Okay, now we got all 3 waveforms there, so we can see them all together, and I can zoom in on those things so we can see them. And yeah, that looks pretty cool. You can see the timing relationships between things. Okay, I can zoom out. The other thing I wanted to kind of point out, which I guess I could have done it before I did this, but okay, on each side you can see the axes for the blue and the yellow trace over here on this side, and the green one's over here. And each one has a set of cursors that I can bring down and kind of look at the voltage there. So it's 14 volts topped off. And this guy here I can bring down to kind of see what the peak is if I want, or maybe if I wanted to see the peak-to-peak ringing of that, I could do that kind of thing. And up here shows the delta. That's 10 volts from peak to peak, and we're going from minus 14.6768 about to minus 24.72, okay, and that's 10.05 volts. So yeah, just kind of wanted to show you some of the things you can look at and use the cursors. There's also ones for the timing relationship too. If we wanted to actually look at the ringing on that, see what frequency it is, I can put one on each peak. And this over here is really high frequency, but this one right here is 5 megahertz. So let's just go ahead and measure. Here, I'm going to move this way. Let's go ahead and measure the frequency on this other stuff, on this one. So grab these cursors, and it gets dampened out. The frequency's probably fairly consistent through there, but it does get dampened out, so I like to go to taller spikes. And right there's 28 meg. Alright, just some interesting frequencies maybe to note. So I'm going to go ahead and turn these things off. I've got cursors over here for the yellow, for the yellow one here, and also one for the blue one if I wanted to get those, and it'll show me in this chart here. And so yeah, and I've got the other cursors for the blue here, so I could put that on the bottom of that waveform, and again yellow, I could do that as well. So pretty cool, all the things you can do and ways you can look at the waveforms and figure things out. One thing I wanted to point out is, here, let me just grab a few cycles here, maybe a couple cycles. Okay, I think that's enough. Alright, so on the secondary side, one thing you may notice, it's some more terminology, some more knowledge about how converters work, is this green waveform is an AC waveform, right? It's on the other side of the transformer, doesn't have a ground reference or any kind of reference until a return, until we put one on there. So it's just an AC waveform. But this top part of the waveform here, let me pull this cursor down again. Whoops, right about there, let's say 13.68. I'm a little bit on the low side, but anyway, say 13.8 volts. That waveform, if I put this down the middle somewhere, say you kind of average it off in there, I'll just stick it right there. It goes down to minus 18.47, so it's not symmetrical around 0 volts, right? And let me do that time thing again. I actually meant to do this when I was showing you that the cursor functions. I got kind of sidetracked, but anyway, so the time I'm putting this somewhere in the middle of this fall time, right about there, I guess. So if we look at the time, the waveform is, say, in this off position, negative, it is about 1.485 microseconds, and we have peak to peak between these two things about 32.27 volts. But really, we have, what I want to say is we have minus 18.47 volts down at 1.485 microseconds. This is volts time relationship. That relates to the positive side. If I go 13.8 over here, and I go, okay, that was 2 microseconds between these. So if I go 2 microseconds, 13.8 versus the higher voltage and a smaller amount of time, 1.48, they should be equal. You have an equal volts. Like, let's say you filled this up with sand, and then you took that sand and you put it up in here, it should fill this. So time and volts are equal on each side. That's why this one's more negative, because it's shorter amount of time. This is less positive, less magnitude than this, because it's longer period of time. I just want to point this volt seconds out. It's a very important relationship, okay? So just want to point that out. Just kind of, showing you some things to look at and teaching you some terminology maybe. So what I want to do is go back to views. I just want to try something out. Let's go to spectrum. And we got a spectrum. We got all three waveforms down here. But I want to get rid of the gate. Okay? So see, when I name them, it's really easy. I know which one's which, so I can go, okay, let's get rid of the gate. As a matter of fact, let's get rid of the secondary. Let's just look at the drain. So we can look at some frequency content here and say, okay, we could spread this out and kind of analyze it or whatever. This is going up to 70 megahertz, it looks like. All right, so we could look at that. And also, sometimes it works better. I'd have to turn this back on and grab more waveforms, okay? And maybe I will have to do that because I want to see if... Hey guys, I hope you're liking this series. Give it a thumbs up. I really appreciate that. You'll notice that I don't get as many views on these design or these power supply videos, which that's my expertise. So I do want to present as much of that as I can. But yeah, you'll notice that the scope review I did got way more views, as well as the multimeter review. So, but I'm mixing it up. I'm doing some audio stuff, audio power supplies. There's a lot of stuff related in there, and so I think there's information that works for the other discipline. So if you're an audio guy, even if you're not an audio guy, you might want to watch those, because I think it helps your power supply stuff is learning this analog stuff. But yeah, so anyway, I'm mixing it up. So hopefully that's okay. I'll try to do a good job of getting the content. You know, sometimes I go too much in audio and I leave out the power supply stuff. I've done that for a little bit, so I'm trying to bring the power supply stuff up. I'm going to throw some audio stuff in there, as well as some reviews. So hope that's okay. Appreciate you guys watching, and let's get on with the video. Okay guys, so what do you think? Was this informative? Was it helpful? Were some waveforms you want to see? I'm going to look at some more waveforms on this. We're going to kind of go through more of the circuitry, and but go ahead and point out things that I'm missing or that you're hoping to see in the next video. And I'm trying to walk through it, kind of keeping the KISS method, right? Giving you the overall, you know, I'm throwing in some terminology in there too. So if you're new to power supplies and stuff, yeah, I understand. Just make notes, write it down. So when I say, you know, I'll mention that it's a buzzword or, you know, new terminology or something like that when it's something important. It might be good to take a note on that until it becomes second nature, or that you have that information down. All right. I keep on looking at things. I've got everything turned off, but I'm always, when I'm this close talking to the camera, I'm a little paranoid. All right, guys. So, yeah, thanks a lot for watching. I want to give 2 thumbs up to my patrons, as always. And there's that super thank you button. There's someone left me, or somebody bought me a cup of coffee this morning. Minesva. I know I butchered that name, but it's just the YouTube handle that they use. But, yeah, I'll put the name right here. Thank you very much. Appreciate that. That's always helpful. It's actually taken me a few days to do this video. They always take longer than I think, but same shirt though, right? Different hair probably. It's probably a giveaway. But yeah, these videos, I had to redo a section of this video. So instead of posting it this morning, I'm redoing it now, and I'll post this very soon. So there you go. Thanks a lot, guys. Oh, and I just wanted to mention that I did review this little picoscope back here, and so I used this. We looked at waveforms on this FLYBACK, which we just now kind of went over anyway, but I might have showed a few different things. I don't know. Anyway, that's in that review. So hope you saw that video. If not, you might want to watch it. It's pretty cool oscilloscope. All right, guys, thanks a lot. And, you know, sometimes I'm showing how to use the scope in that, because if you have a scope similar, many scopes operate the same. The GUI on these picos is just over the top nice. But, yeah, I'm just kind of showing how to use a scope too, so along the way. A lot of people want to know how to use their scopes in real life and real use. And so I'm just kind of pointing that out as I go. So hopefully that's helpful, and I appreciate it. And thanks for watching. We'll see you next time.